Download this code from codegive.com, link in the description below. Lecture 11, Transforming Ambiguous Grammars to Unambiguous Grammars in Compiler Design. In compiler design, grammars play a crucial role in defining the syntax of a programming language. A grammar is a set of rules that specify how to form valid statements in that language. However, grammars can be ambiguous or unambiguous, and this characteristic has a profound impact on how a compiler can parse and interpret the code. What is grammar ambiguity? A grammar is considered ambiguous if there exists at least one string, a sequence of tokens, that can be generated by the grammar in multiple distinct parse trees, or derivation trees. In simpler terms, an ambiguous grammar allows the same expression to be interpreted in different ways, leading to uncertainty about its meaning. Why is ambiguity a problem for compilers? Ambiguity poses significant challenges for compilers because 1. Semantic uncertainty *. If a compiler can generate multiple parse trees for a single expression, it's unclear which tree represents the intended meaning. This can lead to incorrect code generation or unexpected program behavior. 2. Parsing difficulties *. Many parser generators, like Yak, Bison, and Ulr, are based on deterministic parsing techniques. These techniques rely on being able to uniquely determine the next parse action based on the current input and the look-ahead tokens. Ambiguity violates this requirement, causing the parser to fail or produce unpredictable results. Common sources of ambiguity * dangling else * A classic example of ambiguity arises in languages with optional else clauses in if statements. Consider: which if statement does the else clause belong to? The inner if or the outer if? A naive grammar might allow both interpretations. Operator precedence and associativity * arithmetic expressions like 1 plus 2 * 3 can be ambiguous if the grammar doesn't clearly define the precedence, example multiplication before addition, and associativity, example left to right for addition, of operators. Transforming ambiguous grammars to unambiguous grammars. The primary goal is to rewrite the grammar in a way that enforces a single, consistent interpretation of the input strings. Here's a breakdown of common techniques. 1. Explicitly encoding precedence and associativity in the grammar *. This is the most common and generally recommended approach for resolving ambiguity in arithmetic expressions. The idea is to introduce non-terminals that represent different precedence levels. Precedence * operators with higher precedence are placed lower in the parse tree, closer to the operands, effectively forcing them to be evaluated first. Associativity * left associative operators are handled by creating recursive rules on the left-hand side of the production. Right associative operators use right recursion. Example: arithmetic expressions. Let's start with an ambiguous grammar. This grammar is ambiguous because it doesn't specify the precedence or associativity of plus and asterisk. Now, let's transform it into an unambiguous grammar. Explanation *. E represents expressions that can be either an E plus T or a T. This means that addition has lower precedence than the productions that derive T. T represents terms, multiplication and division. T can be T *F or F. Multiplication has higher precedence than addition. F represents factors, which are either parenthesized expressions or identifiers. Parentheses are used to explicitly override the operator precedence. ID represents an identifier, a variable name, etc. Associativity * This grammar implicitly defines left associativity for both plus and asterisk because the recursive productions, E plus T and T F, are left recursive. This means that an expression like a plus b plus c will be parsed as a plus b plus c. Code example, Python with ply, Python lexyak. Key points about the ply example asterisk. Asterisk lexer asterisk the ply.lex module is used to create a lexer, tokenizer, that breaks the input string into tokens, example numbers, operators, parentheses, identifiers. Asterisk parser asterisk the ply.yak module is used to create a parser based on the grammar we defined. The p_* functions define the productions, rules, of the grammar. The docstrings within these functions, e plus t, define the grammar rules. Asterisk semantic actions asterisk the code inside each p_* function, example p0 equals p1 plus p3, is a semantic action. It specifies what to do with the parsed tokens. In this example, we're simply performing the arithmetic operations. Asterisk precedence and associativity are enforced asterisk the parser will correctly evaluate 2 plus 3 asterisk 4 as 14 because the grammar forces multiplication to be performed before addition. Asterisk error handling asterisk the p_error function handles syntax errors. 2 using disambiguating rules, precedence declarations. Some parser generators, like yak/bison, provide mechanisms to declare the precedence and associativity of operators directly, without rewriting the grammar. This is often easier than explicitly encoding precedence in the grammar. Example, yak/bison. Explanation asterisk. Asterisk %left, declares an operator as left associative. Asterisk the order of the %left declarations determines the precedence. Operators declared later have higher precedence. Asterisk with these declarations, yak/bison will resolve ambiguities according to the specified precedence and associativity rules. It effectively generates a parsing table that enforces these rules. Advantages asterisk. Asterisk more concise grammar definition. Asterisk can be easier to understand than explicitly encoding precedence. Disadvantages asterisk. Asterisk relies on the parser generator's capabilities. Asterisk can be less flexible than explicitly encoding precedence in complex grammars. Asterisk may make the grammar harder to reason about independently of the parser generator. 3. Rewriting the grammar to enforce specific structure, for dangling else. For the dangling else problem, a common solution is to create 2 non-terminals, one for matched statements, where every if has an else, and one for unmatched statements, where an if might not have an else. Explanation asterisk. Asterisk matched_stmt ensures that an else clause is always associated with the closest if. Asterisk unmatched_stmt allows for if statements without an else, but forces them to be inside other if statements that do have else clauses. This grammar forces the else to be associated with the most recent unmatched if. Code example, Python with ply. Important considerations for the dangling else asterisk. Asterisk this solution is more complex than the operator precedence approach. Asterisk it precisely defines the desired behavior for nested if statements. 4. Using semantic actions to resolve ambiguity asterisk. In some cases, ambiguity can be resolved using semantic actions, code executed during parsing. This is less common than rewriting the grammar, but it can be useful when ambiguity is inherent in the language or when grammar transformations are impractical. Asterisk the semantic actions can examine the parsed tokens and choose a specific interpretation based on context or external information. Asterisk this approach can make the parsing process more complex and less transparent. General guidelines asterisk. Prefer grammar rewriting. Rewriting the grammar is generally the preferred approach because it makes the syntax explicit and independent of the parser implementation. Use precedence declarations wisely. Precedence declarations in parser generators are useful for simpler cases, but be cautious about overusing them in complex grammars. Document your decisions. Clearly document the precedence and associativity rules that you've chosen, whether they're encoded in the grammar or specified using precedence declarations. Test thoroughly. Create a comprehensive set of test cases to ensure that your grammar and parser correctly handle all valid and invalid inputs. Focus on cases that might be ambiguous. Conclusion. Transforming ambiguous grammars into unambiguous grammars is a crucial task in compiler design. By carefully analyzing the sources of ambiguity and applying techniques such as explicit precedence encoding, disambiguating rules, and grammar rewriting, you can ensure that your compiler can parse and interpret code correctly and predictably. Remember to choose the approach that best suits the complexity of your language and your chosen parser generator. Thorough testing is essential to validate your solution.